I'm based at NASA's Goddard Space Flight Center in Greenbelt, Maryland. I'm a glaciologist and geophysicist studying the Greenland and Antarctic ice sheets, and I help manage day-to-day science decision-making and field operations for NASA's Operation IceBridge. So NASA's Operation IceBridge is NASA's largest airborne mission, and we study both poles, the Arctic and the Antarctic, in an opportunity with the goal of continuing altimetry records between IceSat and IceSat-2, which Tom Newman will be describing after my talk, and with the goal of collecting new information across ice sheets and glaciers in Alaska as well, in the Arctic, so that we can better understand them and how things are changing. We also study sea ice in both the Arctic and Antarctic to understand its extent, its thickness, the snow cover, and how sea ice there is changing as well. Again, with the goal of bridging the gap between IceSat and IceSat-2. So this second slide helps further illustrate that motivation. We have IceSat, which was in operation between 2003 and 2009. And we have Operation IceBridge, which began in 2009 and is currently scheduled to end in calendar year 2019. There's the possibility we might get extended given the prospective launch of IceSat-2 in 2018, but that remains to be determined. This bridges the gap altimetry-wise, but IceBridge can collect many more observations than that. We'll also note that ESA has the Cryosat-2, a radar altimeter, which launched in 2010 and is continuing to operate to this day. So that gives you a visual of why we're here, the primary reason for the mission, which is the altimetry measurements. The third slide is an overview of all the data that we've collected so far, expressed in terms of flight tracks from the various locations that we have operated out of. So on the left, you see the Arctic, and on the right, you see the Antarctic. Because this is IARCtic, we'll focus on the Arctic, and this is updated through the end of 2016. So it doesn't include our 2017 campaign, which recently concluded back in May, but it gives you a sense of the areas that we've tended to focus on. So the Greenland ice sheet, the Canadian Arctic ice caps, the Arctic Ocean, Alaskan glaciers, sea ice north of Alaska, and we do have some missions that we've never flown involving some glaciers in Alaska that we would have done with the P3. Hopefully we'll get those someday. And in 2017, we did actually manage to fly out of Longyearbyen as well, so out of Svalbard. So the coverage is even greater than is shown here now. And many of these missions are repeat missions. So we fly the same tracks year after year to better understand how these systems are changing. And that applies for both the sea ice and the ice sheets as well. Although we do occasionally mix it up. You know, if we want to explore some new areas, observations indicate some regions are changing, that sort of thing. And we have a science team that helps us make those decisions. So the text we have down here, we collect a lot of surface elevation data. We do that using laser altimeters, but we have many other instruments on board too. And we do this with many platforms. In the Arctic, people mostly associate us with the Wallops P3B, which is a fantastic aircraft for long-range science missions. In the Antarctic, it's mostly with the DC-8 out of Punta Arenas. But we've operated on many platforms. It can get pretty hard to keep track of them all sometimes. And we've used nearly 24 instruments at this stage, different science instruments. Some illustrations of LiDAR and radar data down here. So a lot of people use a lot of IceBridge data. I won't dwell too much on this other than say that we do our best to keep track of that. And of course, publications are an excellent metric of how well your mission is doing. This slide needs to be updated. Nathan Kurtz was working on that today. But one of the nice things about inventing a new word for your mission is that it's unique. And so if you go into Google Scholar and search for IceBridge, you get more than 4,000 results. So, of course, that includes conference abstracts as well, but that's a pretty good indication that it's not just NASA's largest airborne mission, it's also one of its more productive ones as well. So we're feeling pretty good about that. This is a slide that I think a lot of people are very interested in, is what is the current state of affairs with the IceBridge mission. So going back to 2015, you can see what planes we flew where. So different rows are different locations and times of year, with the top row here being the Arctic Spring, the main Arctic campaign. But the third row, we also fly the Arctic summer campaigns, which we've done for the last 2 years, and we'll be doing again this year. So where are we in 2017 presently? Well, as I mentioned, we just concluded our NASA P3 campaign, and we'll be having an Alaskan campaign again this year. And we'll also be having 2 Arctic summer campaigns this year. So the goal with these summer campaigns is to, for both the sea ice and the land ice, to capture the effect of melt upon the Arctic region. So in the case of sea ice, the particular focus is to better understand melt ponds, which are one of these features that form in the summertime that can help lead to degradation of sea ice. And we'll be making these measurements this year using the Langley Falcon HU-25. So that's a first generation business jet. We'll have ATM on board the second half of July, operating out of Thule to measure multi-year sea ice north of Thule in the Arctic Ocean. So that's the first of our summer campaigns. The second one will start at the end of August, and there we'll be working with a commercial operator, Dynamic Aviation, to aboard their King Air B200T with the Elvis laser altimeter to better understand the effect of the melt season upon the Greenland ice sheet. We'll be operating out of Thule and Kangerlussuaq in Greenland to measure how much ice was lost between the spring, the beginning of the spring and the end of the summer in the Greenland ice sheet. So we'll be able to map thinning seasonally there in that regard. And that's an advance over previous only interannual campaigns. And we've just started to scratch the surface with these summer data. We'll also have an Arctic campaign this year, possibly 2 of them. And next year, we'll also have an Arctic campaign on the NASA P3 and one again in 2019. And that last P3 campaign is nominally at the end of the IceBridge mission, after IceSat-2 launches, hopefully in the fall of 2018. So that's the master schedule. We'll get into a little more detail on some of these campaigns next. First, we'll just take a look back at the 2016 Arctic campaign. That also involved 2 separate deployments, although we only used 1 aircraft, the Langley Falcon again. First, we operated out of Barrow to measure melt ponds north of Barrow in the Arctic Ocean. And that went quite well. We had 6 flights there. And then later on in late August, we operated out of Kangerlussuaq. We couldn't operate out of Thule because they were repaving. And we had 17 flights there using ATM, FLIR, which is an imaging pyrometer, and DMS, which is a nadir-looking high-resolution camera. And we collected all those measurements. We had 17 flights with the Falcon. It was overall a pretty successful land ice campaign as well. So there we were repeating high-priority Arctic missions that we are baseline missions, the ones we want to try to get every year. And this is a photo illustrating melt ponds, which ended up being used in the New York Times that season. This past campaign that just ended was the NASA P3. We were glad to be back on this aircraft. It had recently been re-winged. So that means what you think. They take the old wings off and put new wings on it, and it extends the life of the airframe. Of course, that means you have to reinstall some of your instruments, and in particular, in the case of the wings, We had to reinstall MEaSUREs, which is the Deep Radar Sounder, Multi-Channel Coherent Radar Depth Sounder is what it stands for. And so that took a little bit of effort, but we did that. And we had our full suite back on board. So we had ATM, Airborne Topographic Mapper, our primary instrument, the laser altimeter. We had 2 versions of that, a narrow scan and a wide scan, MEaSUREs, accumulation radar, snow radars at a higher bandwidth than was possible previously, DMS, again, FLIR, the imaging pyrometer, and we also had, for the first time, an imaging spectrometer, so starting to consider hyperspectral imagery as well. Yeah, and we also had a gravimeter, which was an experimental gravimeter. It was a combination of 2 systems, IMAR and DGS, and that was operated by Lamont Doherty Earth Observatory from Columbia. So that was the instrument suite that was on board. And we ultimately collected 40 science flights in total. There's actually one missing, a very short one, missing from this map. We had our best Arctic sea ice coverage ever, as you can see from this map here. And that was assisted by the good weather, but also by the new coverage that we were able to get out of Svalbard, which IceBridge had not previously visited. It had been previously visited in the early 2000s by the P3 using ATM only, but actually I think the radar was on that too back then, but the instrument suite was overall a big improvement. We had a lot of coordination with other operations, including ESA, CryoVex, OMG, and satellite missions. We underflew CryoSat-2 tracks. That's particularly important for the sea ice. And we also overflew many in-situ sea ice surveys. There was a CryoVex campaign. The US Naval Academy did some work out near Thule. And of course, many sites on the ice sheet, including various core sites, the classic Summit IceSat track, PromIce, many collaborations in that regard with several new instruments. So it was overall an extremely successful campaign. And it was about 10 weeks total. We had a lot of outreach, which hopefully many of you saw. One number that was given to me recently, which I thought was pretty impressive, is more than 2 million people viewed IceBridge content on all our various social media platforms, including a bunch that I'm not on, but I understand are quite hip with the kids. And there is a compilation of the photos available online. It's kept on Flickr, and there's a link there. You can get that later on. But we were very happy with the various folk we had on board with us. If anyone's ever considering interacting with, in particular, Mario Toma from Getty Images, this is photography wire service. And he was extremely successful, not only at getting great photographs of the mission, but of distributing those images far and wide, which was great. Our mission got extended slightly because we were extremely lucky to get an opportunity to host a CODAL at the very end of the mission. NSF organized a congressional delegation tour of US Science Arctic operations. And they went to Alaska, they went to Thule Air Base, they went to Kangerlussuaq, they went to Summit Station as well. And while they were in Kangerlussuaq, NSF very generously gave us a bit of time with that congressional delegation. They certainly didn't have to. And that included 9 representatives of the Committee on Science, Space, and Technology, including Lamar Smith, various staffers, the NSF director, and we had a Goddard science director join us as well. And so we were able to take these representatives on a tour of southwest Greenland. The flight lasted about 1.6 hours. They saw ice, they saw fjords, they saw sea ice, they saw the capital of Greenland, Nuuk, and we discussed with them what we were up to, why people live in Greenland, what NASA Earth Science is all about. It was a very happy thing. It went very well. We were very pleased with the outcome. As you can imagine, if you've ever had to do one of these CODALs, it can be very stressful, the preparation for it, because they can often get canceled at the last minute. Happily ours didn't, and hopefully we imparted to the CODAL the value of what we were doing. So 2017 Arctic summer, I've already described this somewhat, just give you a feel for some of the flight hour plans for what we're going to be doing this summer and photos of the aircraft that we're going to be using. But I've already covered some of this material. So in the interest of time, I'll skip it. Next, I just want to show a couple of slides that illustrate why we do what we do in terms of altimetry. I was asked to put these slides together for NASA headquarters at one point a couple of months ago, but I think they help illustrate the value of IceBridge overall. So before Operation IceBridge, there were various satellite campaigns and a mishmash of airborne missions, and of course IceSat. And they gave us a pretty good sense of where some of the major changes were in the ice sheets and what they might mean for the ice sheet's future. We had some of the first observations of fast thinning, evidence of net mass loss, which wasn't so clear previously, and that some regions can vary over time. Now that we're including IceBridge, we really can better understand how that thinning and in some cases thickening can vary over time and start to connect that to atmospheric and oceanic variables and internal variability within the ice, and to begin to make better predictions of what's going to happen to the future of this ice and how that mass loss will be expressed in terms of thinning. So, when you start thinking about this in terms of time series, without IceBridge data, we couldn't make some of these thing observations that we want, and we'd have a real disconnect in the time series between now and, between the end of IceSat and the beginning of IceSat-2. So we think what we're doing is quite valuable in this regard. And the summer campaigns help give us a feel for the seasonality that we'll observe at length with IceSat-2. Next slide, because I'm running short of time, I'll skip this, but it's a bit of work that I was involved in, but illustrates some of the other things that we can use IceBridge for that can start to help us constrain what's going on beneath the ice in rich ways. So we've been using the radar data to help constrain ice thickness in great detail, but you can also start to constrain other things like, is the bed frozen or thawed? And I'm happy to answer any questions on that. In the interest of time, I'll skip it. I want to point out that NSIDC archives all of IceBridge's data, and the data are intended to be archived within 6 months. In the last year, NSIDC has done a fantastic job of improving their operation. They've reviewed products, they've done a lot of data sanitization, I'll call it, and they're now fully integrated with ESDIS, which that can happily just remain an indecipherable acronym to most of you. But for NASA data archiving, it's extremely important. And it's meant some pretty fundamental changes in how you access IceBridge data now. So I invite you to take another look at it if you can. One of the unfortunate changes from our perspective is there's no longer FTP access, but on the plus side, it's somewhat easier to geofence yourself into the areas you're interested in. So with that, I'll take any questions you have and just show you a pretty photo from some of the data that John Sontag collected. Thank you. Any questions?
Thanks, Joe. This is Shad again. Why don't people write down questions, and then we should have a little discussion section after all three talks to make sure everybody gets time.
Sounds good.
So
yes,
Tom's up next.
You can type your questions into the chat box.
Okay. And I've unshared my screen.
Tom, you can share your slides now.
Okay, can folks hear me?
Yep.
I need to share my screen. Here it is. We'll go there. Okay, hopefully you can see that, and I'll go into presenter mode like Joe did.
Yep, we got
How's
it.
that look? You're good. Very good. So thanks, Joe, for that great introduction. It's IceBridge really has been a great success, and it's kind of funny because Joe is on the other side of that wall right next to me. So Joe, just go ahead and kick the wall if I'm getting off topic, okay? Thanks. The other interesting thing is that IceBridge has been really successful and has a lot of visibility here at Goddard. In fact, my management on IceSat-2 often is asking me for cool pictures from IceBridge, and so I point them towards all these news stories that many of you have seen, and they're super excited about it. Project managers don't really know what an ice sheet is or what sea ice is. So Joe, those kind of outreach events and the media that you guys get and the congressional delegation you hosted, money in the bank. That's great things to do, and we really appreciate it. Anyway, that's enough patting Joe on the back. IceSat-2, we are the other half of the bridge that IceBridge is bridging. And what I'll do in the next 15 minutes is give you guys an overview of what what IceSat-2 is all about and what we're hoping to do. I'm the deputy project scientist on IceSat-2. Many of you know me as a land ice guy, or a former land ice guy anyway. I work closely with Torsten Marcus. He's the project scientist and a sea ice scientist by training. Lori Magruder is our science team lead. She's down at the University of Texas. And Tony Martino is the brains behind the instrument on IceSat-2. It's called Atlas. Ooh, I have a funny title on this slide. This is the wrong presentation. Well, we're going to go with it anyway because I'm partway through it. I'll skip through that one. IceSat-2, of course, is NASA's next generation LiDAR in space, building off of IceSat-1. We're scheduled for launch in late 2018, and IceSat-2 is quite a bit different than IceSat-1 in that we're using a photon counting strategy, and I'll get into what that means. But here we're going to cover the basics of the instrument, some detail on our simulator called Mabel, which collects IceSat-2-like data, an overview of the data products, and some notes on operations. The objectives for IceSat-2 were laid out by the last decadal survey in 2007 to continue the measurements that IceSat made to understand ice sheet changes. It's these first two objectives, estimating sea ice thickness, and also measuring vegetation canopy as a basis for large-scale biomass and biomass change worldwide. As I mentioned earlier, IceSat-2 is going to use this photon counting approach. And what that does, instead of digitizing a full return waveform, it uses individual photons to make the ranging measurement. And what that means is each pulse can be much lower energy, so we call it a micropulse system. And it also enables you to use more than one beam simultaneously. So we're a multi-beam instrument. We have 6 different beams. The high repetition rate I was going to point to, our laser fires at 10 kilohertz, so 10,000 shots a second, and that generates really dense along track sampling. We get one footprint on the ground about every 70 centimeters along track in each of the 6 beams. We have 3 relatively strong beams paired with 3 relatively weak beams, and those different beam energies are designed to increase the dynamic range of the instrument. Now, having pairs of beams, one strong paired with one weak beam, allows you to measure slope in the across-track direction on glaciers and ice sheets, which, as we know, was one of the limitations of the single beam measurement that IceSat-1 was making. A snapshot of what you might see is on this slide. The 6 footprints of IceSat-2 are over here on the right-hand side. The darker green is the relatively strong beams. The lighter green is the relatively weak beams. And the footprints are laid down in a rectangle pattern. By yawing the spacecraft slightly, that's that red arrow, by yawing it by about 2 degrees, these consecutive shots form these tracks on the ground in pairs. And the distance between the strong and the weak beam should be right around 90 meters. We can adjust that on orbit by changing the yaw angle slightly. And again, that goal is to allow us to measure the slope in the cross-track direction on the ice sheet. The pairs are spaced by just over 3 kilometers in the across-track direction. And that was a trade-off with engineering as far as how far apart we could get those beams to maximize coverage, but also keeping the optical design relatively simple. Another big difference between IceSat-1 and 2 is in our footprint size. IceSat-1's footprint was on the order of 50 meters or so. Our footprint should be right around 17 meters, so it's quite a lot smaller. That allows us to image leads in sea ice much better. And then again, the dense along track spacing means that sequential footprints actually overlap by quite a lot. IceSat-2 uses green laser light. So our laser pulse is at 532 nanometers. There are 2 lasers on board, only one of which operates at a time. And that single laser pulse is split on board into these 6 beams before leaving the instrument. The LiDAR on IceSat-2 is called Atlas. The acronym is right up there. And this graphic is a CAD drawing of Atlas sitting on top of the spacecraft. Spacecraft bus is built by Orbital ATK. And Atlas was designed and built right here at NASA Goddard with help from lots of industry partners. Right now, here's the Atlas instrument before it was blanketed. So it looks much less interesting now with it being all wrapped up, but it's good sized. It's a couple of meters on each side. It's like a giant cube. And right now, Atlas is mated to the observatory, to the spacecraft, and the whole observatory is in testing out in Gilbert, Arizona. This is a chart that I keep track of periodically just for my own sanity's sake. What it shows is the months to launch on the y-axis and the month and year on the x-axis. Ideally, the slope of this would be 1-to-1. Each one of these little bumps along the way are a change in our schedule. So last year about this time, we had a schedule change owing to a problem we had with one of our 2 lasers. During testing last summer, one of the 2 lasers failed, and it took some doing to figure out what the issue was and how to fix it. In the meantime, what we elected to do was to continue testing with the remaining good laser. At the end of June, Atlas will come back to us from Gilbert, Arizona. We'll send it back here to Goddard. We'll put on refabricated lasers with the problem fixed and do some testing here at Goddard, send it back to Gilbert to integrate it with the spacecraft and aim for a launch in most likely September 2018. We don't yet have an official launch date, but we should have one of those in the next couple of months. So that's why I say the launch date is TBR, but we expect it to be September 2018. So given that IceSat-2 was such a new concept, a new design, we built an aircraft simulator we call MABLE. And MABLE served a number of purposes. The one I'll highlight here is this third one in the orange box. We are required to have our geophysical algorithms in place at launch to start turning out science quality data as soon as possible after launch. So that means we needed realistic test data to use to develop those. And that's where MABLE came in. MABLE has a lot of similarities with IceSat-2. It has photon counting detection. It's got a very small footprint, about 2 meters. Unlike IceSat-2, MABLE has 2 different wavelength beams, both green and the infrared. Of course, the infrared is what IceSat-1 used, and by having these 2 different color footprints, we can compare how any surface would look when interrogated by 1064 or 532 nanometer laser light. It's also MABLE's lasers are high rep rate. We typically ran them at about 5,000 shots a second. It has a lot more footprints than IceSat-2 will. MABLE can collect data in 16 channels in the green and another 8 channels in the infrared. And typically we operated MABLE with the beam pattern shown here. The beam pattern is actually configurable between flights, but typically we clustered the footprints close to nadir in as much as possible. MABLE flies on NASA's ER-2 or other high altitude aircraft, and that allows it to get over higher than about around 20 kilometers or sort of 90% of the atmosphere to allow us to image what clouds will look like with IceSat-2 data. Here's where we've flown with MABLE over the years. Our big data set for land ice data products and sea ice data products was conducted out of Iceland in 2012. And you can see all these green lines here over Greenland and Iceland. In addition, we flew out of Fairbanks, Alaska in July 2014 to get a look at melting sea ice and wet land ice in Southeast Alaska. All the MABLE data is online. You can go download it from our website, which you can find just by Googling MABLE and IceSat-2, and that should turn up. So what does the data look like? Photon counting data was certainly new to me. It may well be new to you. So I'll walk you through a few examples based on MABLE. This top row is ice sheet data. What we see here on the upper left plot is elevation on the y-axis, distance along track in kilometers on the x-axis, and each one of these dots is a photon that's detected by MABLE. The sun also puts out a lot of light in our wavelength, so we have background light coming in to MABLE or to IceSat-2 whenever the sun is above the horizon. So you see the speckle from the sun, that's the background, but you see this coherent return, and those are the photons sent from MABLE off the ice sheet surface and back up to the instrument again. So then the problem for a geophysical product is to define the surface. A simple way to do that is with a histogram. If you make a histogram of all of the photon returns between the two vertical red lines, you get the histogram shown at the right. You can see the signal to noise is quite good, and the problem then becomes picking where on this histogram are you defining the surface to be. It looks kind of like a waveform. It's got some different information content, but if you're used to dealing with waveforms, a histogram might be a familiar way to look at the data. The second row is sea ice. This is some sea ice north of Greenland, also from MABLE in April 2012. For sea ice, what they're really interested in is the freeboard. And one way to do that is to make a histogram of the photon returns over the rougher sea ice, and then a histogram of the photon returns from the relatively flat leads. And you compare those two histograms here on the right-hand side, and the problem then becomes picking the height of these two and taking the difference to derive the freeboard. Vegetation is a bit different. Trees are diffuse reflectors, and so in this MABLE plot down in the bottom row, you can see ground, you see canopy top, and if you play the similar histogram game, you end up with a picture like this, where you can see the ground return at about 20 meters elevation and a very diffuse return above that. The geophysical algorithms for land and vegetation aim to derive both the canopy top height, the ground elevation, and derived metrics from it. Here's a table of our data products. Now, the low-level data products are all developed here at Goddard by folks on the mission. We think the lowest product most users are going to want to use will be the Photon Cloud, and that's a product that I work on. What that will provide you is a latitude, a longitude, and an elevation for every photon that IceSat-2 collects and telemeters information down to the ground. So you can make those kind of plots we saw on the previous page. The higher level products are led by members of the science community. The most relevant one for this group would most likely be the ice sheet product. The product number is ATL06, and that's led by Ben Smith at the University of Washington, who many of you know. So what Ben is doing is taking an aggregation of photons in his algorithm. He collects 40 meters of photons along track, combines them together to produce one surface elevation posted at 40 meters along track. He's using information from the strong beam and the weak beam together to correct for the cross-track slope, as well as from the distribution of photons along track to correct for the along track slope. And the other geophysical products are shown here with the folks who are leading those efforts. Latency is a question we often get. How fast will we expect to get data out to the public? Our data center, like IceBridge, is NSIDC out in Boulder, Colorado. For the level 2 products, like the ATL03, you can see the latency from the time of collection until release at NSIDC is shown here. The final L2 is a ballpark of about 3 weeks. I'm sorry, the initial L2. And then the final L2 is a couple of weeks later. So we do have a quick look product planned for the Photon Cloud. The higher level products take a bit longer, but the bottom line is that from date of collection until date of release, we expect it to be about a month and a half. We'll know more, of course, once we're on orbit. Yeah, and it'll take a little bit of time, no doubt, to work out the wrinkles in the data flow and the data processing. You do your best guess you can ahead of time, but of course, the real data is going to look different in some ways. So a table of data volumes, it's a bit of an eye chart. The take home here is that if you're dealing with any of the data products at the photon rate, it's a sizable product. ATL03, we expect to be in the ballpark of about 500 gigabytes a day. But again, that's providing a latitude, a longitude, and a height for every photon we detect. ATL06 is the land ice product, and so that aggregation of all that photon data into a 40-meter product posted at 40 meters is quite a bit smaller, in the order of 4 gigabytes a day or 5 gigabytes a day, a much more manageable size. That's the total size for both ice sheets in the Arctic and the Antarctic, as well as a number of mountain glacier areas that will flow through the ATL06 processing chain. Oops. Skipped one. Our orbit, about a 500-kilometer altitude, but a different inclination than IceSat-1. We'll go up to 88 degrees north and 88 degrees south, so it's a 92-degree inclination. Over the polar areas, when we're taking ice measurements, we're going to follow the strategy of IceSat-1 and operate in repeat track mode. So we'll be pointing at the same patch of ice as close as we can every 91 days. So 4 times a year, we will visit a particular track. Over the mid-latitudes, the ecosystem science community is aimed to do the most dense mapping they can. So we'll execute a sequence of off points every 91 days to make as dense a mapping as we can over 2 years. Here's an example of what that looks like. The first 91 days, we'll point at the heavy blue lines right over here. And after 91 days, the track spacing between these two at the equator is on the order of about 29 kilometers. 91 days later, instead of pointing at the same blue lines again, we'll off point to split the difference between them, reducing the off point or the track spacing from 28 or so kilometers to 14 or so kilometers. Every 91 days, we'll keep splitting that difference such that after 2 years at the equator, the track density should be on the order of 2 kilometers. Of course, this is just where we're pointing. It's not necessarily where we're getting data. Things like clouds limit the penetration of green light from the spacecraft to the surface and back again, as does dense canopy. Places like Brazil with a triple-decked canopy will be a real challenge for IceSat-2 to get photons all the way through to the ground level and back again. We expect in some of those places we won't see the ground. In other places, the canopy is very open and we'll get very few photons from the canopy. And so in those areas, we'll be able to measure the Earth's elevation very well, the ground height, but we'll have a much larger uncertainty on the tree height. Cool, so this is my last slide. As we've gone through testing of ATLAS over the last several years, the predicted performance of the instrument is consistent. We are in observatory testing now, and the kind of issues we're coming across are almost entirely related to the ground support equipment and the ground support networks. But ATLAS is behaving as it's designed. The laser repair is well underway. Those 2 repaired lasers will be back here at Goddard the 1st and 3rd week of August of this year. The data product implementation is well underway. We've been working on that for a couple of years with our science team. Those algorithms, regardless of who they're written by, are all coded and implemented here at Goddard so that when the data comes from ATLAS and from the IceSat-2 spacecraft, we generate the products here at Goddard and then send them off to NSIDC for everyone's use as soon as we can after that. And that's all I was going to say, and I'm happy to take any questions through the chat box at the end. Thank you, and I appreciate the opportunity to tell you guys about it, and it's great to see so many names of folks I've worked with over the years, so hi.
Thanks, Tom. That was great. Let's transition to Ian. We've got 20 minutes left. Ian can talk for a few minutes, and then we'll have a few minutes for question and discussion, which hopefully we can make happen. Ian, are you still hanging around?
Yeah, yep, I'm here. I'll just get it screen shared. Okay. Does that look good? Anybody confirm? Thumbs up? All right. So I'm just going to talk really quickly about the Greenland Ice Mapping Project, or GIMP. This is really Ian Jockin's project, but he had something better to do, I guess. So I get to describe it. But this is now in its almost 10th year. This is a NASA MEaSUREs project. So these are in 5-year cycles. And basically, it's all about mapping Greenland's ice sheet change to the highest spatial and temporal resolution we can from space. And so the highlight, or this, Ian put most of these, the other Ian put most of these slides together, so they're kind of radar centric. But a key part of this and kind of what the project was built around was this ability to do wide area mapping with originally the RadarSat satellite. And so this was the original series of data we got. And these are 500-meter resolution velocity fields covering the ice sheet almost annually now since 2005. And now with the addition of Sentinel-1, TerraSAR-X, and some ALOS data and Landsat 8 data is in there as well. So we get kind of a wide area coverage, these kind of annual mosaics from that. So that's data product number one. Let me just go right back. Just make a note of the URL down there. You're much better off just going to the NSID website and looking at that URL to get a description of the data than you're going to get from me right now. So go ahead and just do that and mute me. But this is just an example of the data that you get from GIMP, from at least the radar products. So this is Jakobshavn Isbrae. This is a series of samples along the glacier, the main glacier of Jakobshavn, the fastest moving glacier in the world, I think. And this is the long time series that we get from GIMP now. Actually, this is kind of faulty advertising. Again, this is Ian's slide. Some of this data, the radar data before 2005 or so, isn't actually in GIMP, so I'm not sure where he's getting that, but this is what he wanted to show. You can get it from the optical data anyways. But you can see the change through time at Jakobshavn, the big acceleration, and then the big seasonal variability going through different phases of retreat that we're well accustomed to now, or know a lot about now. One addition to GIMP was the ability to get very high resolution, frequent repeats from TerraSAR-X and TandemSAR-X data. And so these are the coverage of Tandem and TerraSAR-X isolated footprints over the ice sheets. You can see most coastal outlet glaciers have at least 1 to 4 recoveries per year, up to 10 at some of the bigger outlets. This is what we're getting now from Sentinel-1. So that's not actually in the GIMP set yet, but it's going to be in the next few months. So this is just an overview of the various recoveries from radar, satellite radar. Sentinel-1 gives you broad coverage, so it's a really nice new product for lots of repeats. We get 6 to 12 day over the entire ice sheet velocity. So that's going to be a very dense sampling. Of course, this is radar, so it's all weather, all season. And then TerraSAR-X, TandemX gives you much better resolution, but at the trade-off of less temporal resolution and coverage. So now just to talk about what I actually do for GIMP, which is the optical data processing. By optical, we mean Landsat, Aster, and now Sentinel-2 feature tracking. This is an example of Jakobshavn from 1985. So this is the kind of quality data we can get from one of the early Landsat 4 thematic mapper. So we're going to be extending GIMP all the way back to the mid-80s. And of course, this data record now continues to today with Landsat 7 in 1999 and the Landsat 8 more recently, with the density of coverage getting pretty intense now. So these are the kinds of time series you can get for various glaciers around Greenland. Allison Glacier, the full time series since 1985, with the big speed up over the past few years. And this is the combined optical and radar record. And you can zoom into just the past few years and see how dense a record that is. And then some other glaciers in Greenland. So these glaciers can't really sneeze without us knowing about it at this point. And then so some other products they don't have time to talk about. Of course, the GIMP DEM. There's a version 2 out now. These are 30-meter DEMs of the entire ice sheet. The new version actually has the ability to do DHDT from. It's got quarterly mosaics of data, so you can go and difference them and get the changes in elevation. There's also radar amplitude images to look at things like melting and changes in glacier facies. And then we have digitized termini, annual digitized termini of outlet glaciers, so you can look at glacier retreat. Here's just the last slide I have is an example of the elevation changes you can get from the GIMP DEM, the version 2 DEM now. So this is actually the coast of southwest Greenland by Kangerlussuaq. There's Russell Glacier kind of in the middle there. And so this is the difference between a few years, I think 2013 to 2015 or so. And so you can see the thinning over the ice sheet, whereas over the land, there's no change. So this is the kind of resolution you can get. So that's all I'm going to show right now. Please go to the website of the NSIDC and poke around. If you have any questions, feel free to get in touch with me. Don't flail around. We usually have the answer to what you're looking for. So yeah, don't hesitate. Thanks a lot.
Thanks, Ian. That was fast, as usual. So we've got 10 minutes for a discussion. Does anybody have any questions or comments for any of the speakers? Don't be shy.
And remember that you will need to unmute yourselves for us to be able to hear you.
Hey, Ian, I got a question for you. Oop, can you hear me? I don't think
Yeah, you're on, Tom.
Okay, cool. So Ian, going forward, what does it look like for GIMP? You guys do this work on a time available basis, or do you guys have some longer term look ahead to sort of the next 5 years of what you're hoping to do?
Funny you should mention that. We just submitted our proposal for renewal a couple of weeks ago. So they're in 5-year cycles. Our current GIMP 2 runs out next year, so there'll be data produced through spring of 2018. And then, of course, if our proposal is successful, then we'll extend through 2018 plus 5, so 2023, 22, something like that. And so within that time frame is really exciting. We're expecting NISAR, besides IceSat-2, also NISAR to be launched, which will really be the game changer for mapping the ice sheet, make our job really easy. But yeah, we're just going to keep adding sensors as they come. Sentinel-2 and Sentinel-1 are providing a huge data stream that we're still kind of grappling with, dealing with. So that's going to be the next big event in the next year or so to add that data.
Ian, I have a follow-up question for you.
Okay.
I'd like to understand the difference between GIMP, which focuses on Greenland, and Arctic DEM, which does the whole of the Arctic. Who should I trust more in Greenland?
Well, you don't have to trust either because it's the same data actually. So you can think of GIMP as a downstream of Arctic DEM. So you can think of Arctic DEM as the mission, and GIMP taking the data like we take RadarSat data or Landsat data and then putting it into a more refined, higher level product. So it's actually the same exact data. It's just registered to IceBridge. It's filtered a bit in a different way. It's stacked and mosaicked in a different way. And that's pretty much it. We apply the GIMP masks and stuff. So really it's just a more refined product, but the base DEMs are the same.
Okay, so things like some of the artifacts in the Arctic DEM mosaic for Greenland, those are gone in GIMP 2?
Hopefully. So GIMP, or I'm sorry, Arctic DEM is a completely automated product. Okay. So everything in it is filtered automatically. I have to be really careful what I say because Claire's watching and I don't want to make her mad. So you could kind of think of it as a more raw product. And certainly if you're doing kind of geodetic level work, you don't necessarily want to use the Arctic DEM mosaics. Yeah. Those are meant to be more of an overview product. Yeah. They're registered to IceSat so that there might be co-registration, temporal issues there with co-registration. So you're best off either using GIMP if you want kind of a broader coverage, 30-meter resolution, or going to the actual Arctic DEM 2-meter strips, the individual strip data, and using that if you really want to do all the work.
Okay.
Yeah.
Great. Thank you.
Thanks for those questions. This is actually interesting. Next month we're going to have Tom Wagner and Pat Heimbach, who's listening, and Ellen Enderlin are going to talk about combining observations and models and providing constraints for models. And I was wondering if any of you three who spoke today want to comment about if in the design phase of these remote sensing campaigns you're thinking about how these data are used in ice sheet scale or basin scale modeling.
Well, I can speak to that from the IceBridge perspective, and paraphrasing the science team to a degree, that they most definitely are considered as topics when designing IceBridge missions. So we focus on a lot of repeat track missions, but there is also the imperative to extend our coverage in such a way that we can fill in gaps in existing records across the ice sheets. That's easier to do for the Greenland ice sheet than the Antarctic, but it is a factor that's considered. And sometimes missions are designed such that they can focus on specific processes that either science team members are interested in or they recognize there's a community interested in, often having to do with outlet glaciers, for example. So with IceBridge, we have that flexibility from year to year, and the science team can prioritize as they like. And, and that has resulted in larger scale products. For example, MEaSUREs Morleyham's mass conserving bed across the entirety of the Greenland ice sheet. Does that answer your question, Chad?
Yeah, that's very helpful.
Yeah, I should also emphasize, from an IceBridge perspective, we're always open to new ideas for where to survey. There's no harm in asking and contacting members of the science team. It's on the website, and advocating for specific lines. And if they mesh with IceBridge interests, then they'll be considered and prioritized appropriately. It's certainly possible. I mean, it regularly happens. A good example is like overflights of cores. Now, that's not speaking directly to ice sheet wide kind of initiatives often, but it regularly happens. I mean, we overflew Clem at least a couple times this year. I know that.
That's a pretty good thing for everybody to know about, that asking never hurts. Tom, do you have any comment on that with respect to IceSat-2?
Yeah, IceSat-2 just has the altimeter, so it's it doesn't have the full, not nearly the full breadth of instrumentation that IceBridge brings to the table. With respect to supporting modeling, the denser coverage of IceSat-2 in terms of number of tracks, ideally we run continuously, not in campaign mode. So we should be making high quality elevation measurements that can be used either by models directly or integrated into efforts like the Arctic DEM as control points to make better DEMs for modelers to use. Similarly, we do have the capability of off-pointing IceSat-2. We're working on making it easy for science users to request off points. If you have a field campaign, or if you have some area that whatever reason you'd like an IceSat-2 track over, you'll have the means to request that, and that'll put you in touch with the Project Science Office here to execute that for you once we're on orbit.
Great, thanks. Ian, you got anything to add?
Sure. I mean, there's lots of papers out there now using GIMP and GIMP-like products to constrain ice models, ice flow models at everywhere from the individual glacier scale, looking at processes, right up to the large-scale continental ice sheet models. In fact, a bunch of us were on a paper that just came out a little while ago by Steve Price, who developed a framework for putting all of these data into a big pot and using it to constrain a model, and particularly their model at Los Alamos, and that includes IceSat, both generations, and the GIMP data. And I think us observationalists and remote sensors, I think every proposal we write now, we're well aware that there needs to be at least a page devoted to how this data will be directly implemented into a model, and even better, have at least a collaborator ice sheet modeler on the proposal to show how that's even more of a commitment. So I think this is something that's happening. I think the ice sheet modelers are still working to figure out how best to assimilate the data, or at least use the data to validate their models. That's a lot of work in itself. So right now the effort on our end is getting the data into something that's usable for the modelers and easily ingested into the model. That's the big push of effort on our part right now.
Great. How about some of the modelers that are listening? I see Liz and Andy and Patrick are listening. How are we doing as observationalists? Are we giving you what we need, or are you guys silently screaming at us to give you something different that we have the capacity to give to you, but we just refuse to do it? Or where should we be focusing our attention and developing new kinds of observations that would help you?
This is Andy. Can you hear me? Okay.
Yes.
I think Tom just said we as modeler, or maybe I can only speak for myself. We're in the process of trying to find out how to deal with these new large data sets that we have. So right now we're really trying to ingest and figure out what the models can do with all the data that we could use for validation and data assimilation. And I don't know what the stage is for the rest of the modeling community, but this is a large piece of work, and myself, we're included. We're playing around with different methods, but right now I'm not I cannot give you like a direct answer and say, this is what we need. We need it in format A, or this is the time resolution that we need. We are really almost at square one, trying to set up the data flow that we think could yield to improvements in the ice sheet models. So I'm afraid I cannot give a very strong answer at the moment, except that we're working on that, and hopefully have more to say in the next couple of months, or maybe year or two.